In this video, we will continue to discuss angular motion, specifically objects that are moving in a circular path. Let's start by discussing how forces are used to make an object curve and move in a circular path. To do this, let's consider a basketball that is rolling on the floor at speed v like this. In this view, we're looking down on the ball from above the floor. If there are no horizontal forces acting on the ball, then it will continue to move at speed v in a straight line, so that a moment later the ball will be here and still rolling at speed v. As we know, if we apply a force in the direction of the ball's velocity, say we push it this way, then the ball will speed up. Or if we apply a force opposite the ball's velocity, then the ball will slow down. But if we apply a force that is perpendicular to the ball's velocity, then the ball will not speed up or slow down, but it will change direction, say this way. If the force was only applied at that instant to make the ball change direction and then was removed, then the ball will begin to go straight again so that a moment later it will be here, and it will still be traveling at the original speed since the force was applied perpendicular to the velocity. Now we'll push momentarily on the ball again with a force that's perpendicular to the ball's velocity again. Once again, the ball's direction will change like this, but since the force was applied perpendicular to the ball's velocity, the ball won't change speed, and so a moment later it will be here and still going at speed v. So we'll continue this process of applying a force periodically that's perpendicular to the ball's velocity, and each time the ball's direction will change, but its speed will not change. So here's the new force, and the new direction, it winds up here, and then a new force, a new direction, and so on. And so the ball continues to go around, making a circular path. And now the ball is returned back to its original position. And if we continue to apply a force that's perpendicular to the ball's velocity, then we can continue to make the ball go around in a circle. In this example, to explain the concept, I just applied the perpendicular force at discrete moments, so the path of the ball was actually an 8-sided figure rather than a nice smooth circle. If instead of applying the force at discrete moments like this, we applied the force continuously and always perpendicular to the ball's velocity, then the ball will in fact move in a nice smooth circle. Here's a demonstration of doing that with the basketball. Here's the basketball rolling at a constant velocity, and after a moment it winds up here. As we did before, we will apply a force that's perpendicular to the ball's velocity, but now we'll apply the force continuously and rotate it so that it's always perpendicular to the velocity of the ball. Notice how the force is always perpendicular to the velocity, and the ball's speed never changes because it's perpendicular. Also notice that the force always points towards the center of the circular path. Other examples of objects moving in circular paths are a ball on a string, where the tension of the string provides the force that's perpendicular to the object's velocity, or the Earth going around the sun, in which case the gravitational force provides the force that is perpendicular to the Earth's velocity, or a car going around a curve, in which case friction applies the force that's perpendicular to the car's velocity and makes it curve. There are two major points to make based on what we've discussed so far. A net force that's applied parallel to the velocity of an object, that is to say, tangent to its path, will cause the object to change speed, but it will not cause the object to change direction. And a net force that's applied perpendicular to the velocity of an object, that is to say, perpendicular to its path, will cause the object to change direction, but it will not cause the object to change speed. Because the effect of a net force that is perpendicular to the velocity is so different from the effect of a net force that's applied parallel to the velocity, we will often redefine our coordinate scheme for circular motion this way. The tangential axis is parallel to the object's velocity, where the positive direction is in the same direction as the object's velocity, and the centripetal axis is perpendicular to the object's velocity, where the positive direction points towards the center of curvature. As you might imagine, this means the coordinate scheme is constantly rotating with the object. Here's an example to demonstrate this. Here we have a ball tied to a string, and someone is swinging the ball around in a horizontal circle, say in the clockwise direction. If we neglect air resistance, then the net force on the ball as a result of the string is here. And since it is perpendicular to the ball's velocity, then the ball curves in the path shown. Now let's apply the coordinate scheme. The positive tangential axis is here, pointing in the direction of the velocity, and the positive centripetal axis is here, pointing toward the center of the circular path. Now as the ball goes around the circular path, all of the vectors and the coordinate scheme will rotate with it like this. And we keep going around, and notice we just keep rotating the tangential and centripetal axes all the way around. The term centripetal means center pointing, which is appropriate as the axis points towards the center of the circle, and the term tangential is used because the axis is parallel to the velocity, which means it's also tangent to the path of the object. Just as we separated vectors into x and y components before, we now separate vectors into centripetal and tangential components. In the figure, the net force is only pointing in the positive centripetal direction, so it doesn't have a tangential component. But let's look at another example. Here's a car going around a curve. At the instant shown, the car has a velocity in this direction. In order to curve and stay on the road, a net force must be applied perpendicular to the velocity, like this. The actual force that pushes the car this way is the friction force between the car's tires and the road. The driver causes this friction force when she turns the wheel and turns the tires. If the car's tires continue to be turned, then the friction force, and therefore the net force, will continuously rotate, like in the basketball and the ball on the string examples, and the car will follow this circular path. At the instant shown, the tangential and centripetal coordinates are here. Since the net force is only in the centripetal direction, the car will not speed up or slow down. Now let's consider the scenario when the driver brakes while turning. At the instant shown, the car again has a velocity to the right, so the tangential and centripetal axes are the same as they were before. If the driver is braking as well as turning, then the net force on the car, again caused by the friction force, will look something like this. Now the net force has components in both the centripetal and tangential directions like this. The component in the tangential direction is in the negative tangential direction, that is to say opposite the velocity, so it's causing the car to slow down. The component in the centripetal direction causes the car to curve, so again to follow this path. The centripetal component of the net force is often referred to as the centripetal force. But keep in mind that it's the component of the net force, not just an individual force. The other important thing to recognize here is that, according to Newton's second law, if there is a net force, then there is an acceleration as well. We can calculate the acceleration, both the magnitude and its components, by applying Newton's second law and dividing the net force by the car's mass. And so the same vector triangle can be used to represent the acceleration vector. Just as the centripetal component of the net force is referred to as the centripetal force, the centripetal component of the acceleration is referred to as the centripetal acceleration. There is a very useful equation relating the centripetal acceleration and the velocity. The textbook provides a derivation for this equation, and here's the result. Centripetal acceleration equals the speed squared divided by the radius of the curved path, r. Since we also know that v equals r omega, centripetal acceleration also equals this, r times the angular speed squared. So let me summarize the equation here, where you can see all of the components of the equation clearly spelled out. So that brings us to the end of the video on centripetal and tangential force and acceleration.